students, so we have discussed a lot about steels and their microstructures in the last 2 weeks. So, I am going to start on cast iron this week, and we are also going to spend about 4 or 5 lectures on different discussions regarding cast iron. But before I do that, let me just remind you that in the last class I have discussed with you a very important concept, and that is the TTT diagrams for steels. TTT diagrams are very important, not only for the scientist, but also for the people or for these engineers working on the shop floor. And these diagrams are important for different heat treatment processes of steels. So, it is required that you understand how to read this diagram and interpret. So, I will just spend about 5 to 7 minutes on these diagrams, then I move on to the cast irons. So, this is a typical TTT diagram of 1080 eutectoide steel. That means, this is a plain carbon steel consisting of about 0.8% carbon. So, now if you look at this diagram, there are 2 axes, temperature on the vertical, time on the horizontal axis, right. And as you see that on the right side on the vertical axis, we have also plotted temperature in Fahrenheit, and the left side we have plotted temperature in degrees Celsius. And inside whatever is there are in different colors. First of all, the things which is looking like a C shaped is what is more important, and as you look at it, this is the A1 temperature, many times AE1 temperature. A1 temperature is the eutectoide transformation temperature, above which austenite is stable. Below that temperature, austenite is not stable. We have seen austenite can undergo 3 different types of transformations: austenite to perlite, austenite to benite, and austenite to martensites. And you can also have mixtures of perlite plus benite, benite plus martensites, and martensite plus austenite as a retained austenite is possible. So, what you see here is this curve, this one, the left side of this curve, it shows you the beginning of the paralytic transformations, or beginning of, rather you can say, transformations which are perlite or benite, and the right side one is basically called end. So, beginning means 1% transformed, 1% of austenite got transformed, it can be perlite or benite, and end means 99% austenite has got transformed, and in between you have also a curve 50% transformed. So, and then that is the one part of the diagram. Next part of the thing is you have a martensite start temperature, martensite 50% transformation temperature, martensite 90% transformation temperature. They are well below the paralytic or benitic transformation temperatures. So, this is what is the actual diagram looks like. I am not going to go back and then tell you how this diagram has been obtained, that I have done a lot in the last few lectures. I am just only going to tell you that how to read it. So, these are the important curves which you need to know. Now, as this is a plot between temperature versus time, we can actually plot different cooling rates. Cooling rate is nothing but dt, d capital T by d small t. This is what is cooling rate, right. So, that is nothing but d dt temperature. So, that is the slope of this curve. As you see here, I have drawn 4 different lines, each one signifying a cooling rate. So, let us first start with the slowest cooling rate. So, that is this line, I am drawing it again. If I cool it slowly, very slowly, I am cooling actually at about 100 degrees from suppose 723 to 623 or 650 Celsius in about say couple of 100 times, 100 seconds times. So, about 600 times, 600 means 1 hour, sorry 600 means not 1 hour, 6 minutes, 10 minutes, sorry, 10 minutes, 600 is 10 minutes time, a very slow cooling rate. So, that means one is about 90 divided by 600, that means it is basically very low. 90 divided by 600 is how much? Is 9 by 60, 3 by 20, that is very slow cooling rate, correct. Even less than 1 degree per minute or 1 degree per second. Okay. So, it is, or if you consider minutes, it is basically about 9 degrees per minute, that is not fast, that is very slow. If you cool it that slow, what will do? If you cool it this slow, the cooling curve will cut the start or beginning of polarity transformations, and because of this we are going to have polarity transformation started, and the polarity transformation will keep on going on, and it will lead to formation of coarse perlite as you see here, and coarse perlite means interlaminar spacings will be very high for the perlite, and the hardness will be RC 15. If you cool a little faster, let us suppose if you cool about say 20 degrees per minute, then you will also form perlite because it will pass through this polarity transformation curve, but it will be fine perlite, hardness will be almost double the RC 30 or RC 40. Now, if you cool it differently, there is a third curve, if you cool it fast initially to bypass the nose of the beginning curve and keep it there for long time, then you will have magnetic transformations, and this magnetic transformation is lead to formation of banites in the form of upper banites, because it is at the upper temperature 450 degree Celsius temperature. On the other hand, so that means what? If I cool it quite fast initially to bypass the polarity transformation and then keep it isothermally for a long time, I am going to start the magnetic transformations. And the last one is basically this one, you see here the very fast cooling. If you cool it very fast, okay, you are cooling 700 to 200 Celsius, 500 degree Celsius temperature in about say 5 seconds. So, that means 40 degree per second, that is a very fast cooling, that means 40 degree per then 24 240 okay 60 2400 degree Celsius temperature per minute. So, in a few seconds you are getting the sample temperature going down to room temperature from 700, that is a very fast cooling. And if you do that, you bypass the nose, bypass the magnetic transformation, what you land up is basically in the magnetic transformation regime, that is MS start, and you form martensites. Depending on how much you cool, how fast you cool, martensite transformation will stop at 50% or 90%. So, these are the way these curves to be written. That means, if you want to generate a particular microstructure for a particular composition of steel, you get these TTT curves of the steel from different sources and then draw these cooling curves, and then you will understand whether you have to go for air cooling or water quenching, oil quenching, or water quenching and then followed by isothermal holding at magnetic transformation. That is what is your requirement. You can produce mixture, you can form certain fraction of martenites and quench, it will form martensite, rest of the austenite. Suppose if you cool it like this, hold up to this point temperature and quench, what will happen? You will have banite plus martensite mixture, correct. Okay. So, as you see here, the cooling rate is very high for martenite transformations. So, that means what? You have to quench very fast, and if you quench the sample, you will form thermal stress, and thermal stress will lead to formation of cracks, sample will break. So, therefore, to avoid that, we want to reduce the cooling rate, or rather we want to make the cooling slow. So, to do that, you have to add alloying elements. So, if you add alloying elements, what the alloying element do is basically they shift this nose of the curve to the right side. So, earlier this was the cooling rate, you see earlier curve was like this was the critical cooling rate for martenite transformation, now this has become the critical cooling rate. So, you can see which one is slower very easily. So, that is why we add manganese, why we add chromium, we add tungsten, we add many other stuff to reduce this cooling rate for martenite transformations. That leads to not only that, it will also slow down the polarity transformation cooling rate. You see here, this is what the polarity transformation cooling rate is also very slow, correct. So, this is exactly the whatever I told you I am showing here for 0.2% carbon steel, that was 0.8. So, only thing it will change is that the shapes will remain same, only thing it will change is the position of these curves, because carbon is also alloying elements. but not like other alloying elements. Carbon is, steel metallurgy, we do not consider carbon to be alloying element as a part of alloying element like moly, like tungsten, like manganese. Carbon is different, we consider. Okay. So, now this is what is with the microstructure. Many times you will find such a kind of diagrams. Temperature is Fahrenheit versus time. You see here this is austenite, metastable austenite, you can have perlite, you can have benite, you can have martensite at different tones. So, if I cool it down like this, I will form martensite. If I cool it down like this, I will form perlite. If I cool it like this and hold it, I will form benite. That is the way. So, you can represent this diagram in many ways. Fine. So, another way of doing this is, yes, there are a few more things I will say. There are different kinds of coolings. One is the cooling rate, other one is the way of cooling. If you furnace cool, this is what is the slowest cooling rate possible, you will form coarse perlite. If you air cool, take the sample out from the furnace and keep it in air, you will form, this is the cooling rate, you will form fine perlite. If you cool it like this and isothermal hold for a long time by what is known as Oss-tempering. Oss-tempering is what? You transform the austenite to benite, that is called Oss-tempering. So, to do that, you cool it, quench it like this, isothermal hold it at about 400 degrees Celsius temperature. Now, if you cool it water quench, you bypass the nose of this curve, Pauli transformation curve, you form martensites. But cooling is very fast in water quench, you will slow it down by oil quench depending on how is the nose situated. The nose is very close to the vertical axis, then you have to go for water quenching. If it is not so, you can go for oil quenching. There is another transformation, very interesting, what is known as martempering. You cool it, okay, keep it there so that you form martensites, so that you have formed little bit of benite and then you quench it, correct. If you quench it, rest of the austenite will form martensites. So, this one will lead to lower benite plus martensite. So, you can see you have varieties of cooling paths possible and you can impose, you can actually ingeniously generate different kind of cooling situations, cooling rate situations and create different microstructure. That is the beauty of steel metallurgy. In steel, the properties of the steel can be monitored many ways, that is what is not understood by the physicist or the chemist compared to metallurgist. Okay. Very lighter side, this is what I can say, because we can take the same composition of steel and we can change this heat treatment parameters, we can generate different microstructure and by different microstructure we can have different properties. And that is what is our end game, right. You want to have properties of the material which is useful. So, to obtain that, basically that things we simply can have different cooling rates mean different environment, different ways of changing the microstructure. That is what is done in the heat treatment of steel. Okay. I do not want to go into this is what is this aspect of alloying, so that is not required. Okay. Now, so far I gave you again an amount of knowledge or basic understanding of the CT2 curves. Now, let us move it to the cast iron family. Cast iron, like steel, is also very important material. In fact, if you go to automobile industry, cast iron has a lion's share in the automobile industry. Okay, not the steel. Cast iron is widely used in automobile industry, cars, trucks, and many other things, trawler. This is what is the material used to make different components, and I don't want to give it. It basically has a very large share. So, therefore, it is important that we understand. But difference between steel and cast iron is that steels have very low carbon. Okay. That is the first thing. Steel contains about maximum 1% carbon, 8% carbon, and majority of the steel contains about 0.2 to 0.5% carbon. On the other hand, cast iron carbon concentration is much larger. It can be 2.5 to 4.5%. That is the first difference. So, they are iron carbon alloys, but they are not same as steels, cast irons are. Second important issue is that we have a lot of silicon in cast iron, which is not there in steels, except spring steels, where we intentionally add silicon to increase the elastic strength. Almost all the steels will not have much silicon. Other than cast iron will invariably have 1% or more than 1% silicon, and here silicon is required. I will explain you why it is required. Okay, so as you know, cast iron also has varieties like steels. So, you can generate different microstructure in cast iron, that is the beauty of it, and that is why they are very interesting. and you need to understand, like here white iron, malleable iron, gray iron, ductile and nodular iron, 4 different types of cast iron I am showing in the picture. So, you see here these are the 4 different, there are many more, there are actually like vermicellar cast iron or alloy cast iron, which we will discuss maybe in the after some time, but not today, correct. Now, let us discuss what is this. So, this is again in a brief snapshot, this is white iron where you have no graphite, and then gray iron where graphite is like a flex, nodular iron or spiral graphite iron where graphite is like a nodule, and malleable iron where graphite is like a tempered or graphite is like irregular shapes, correct. So, basically what in gray iron, nodular iron and malleable iron we change the graphite morphology, but in case of white iron what we have is basically cementite, not a graphite at all. Let us now discuss in terms of phase diagram, because this is a course on phase diagram. So, you have to understand that. So, as you see here, this is the iron carbon phase diagram, normally people tell, but this is not, today we will come to know. So, as you see here, you have perlite A1 temperature below which the perlite transformation happens, that is called alpha plus cementite, I discussed a lot about it. Then you have austenite or gamma, correct. Then you have cementite on this side. So, these are the carbon concentration 0.8, about 2.01 percentage, this is about 3 percentage carbon. So, this is what is it. Now, you know, this is the region on which steels were discussed. Only thing about steel I did not discuss, which I will do, is this peritectic reaction. I told you for low carbon or stainless steels, we have a chapter on stainless steel where this will going to come into picture, but I have discussed about the whole thing. Now, cast iron forms, so therefore, this is the region of steel, right. You can see here I have marked by a blue box, sorry, green box. Now, this is the region on which cast iron composition falls, as I said 2.5 to 4.5 percentage. So, the important reaction which happens in this region is the eutectic reaction which is taking place here. From the phase diagram perspective, we have to understand that reaction. On the other hand, for the steel, important reaction was eutectoid transformation reaction. That is what we have done. We have seen how austenite transforms into perlite, martensite or marite, but here the most important issue is the eutectic reaction, which is basically can be liquid going to gamma plus cementite or liquid going to gamma plus graphite. Okay. These are the 2 reactions which are there. Now, this is the diagram which I have got from Professor Masalski's book called binary alloy phase diagrams, and here you see there are 2 types of curves, one solid one, other one is the dotted one. Okay. Now, I spend about 5 minutes to explain you this is very important, then we will go for the cast irons. As you see here, the black ones are the solid lines are basically for iron carbide equilibrium, that is what is Fe3C, you see here iron carbide. So, therefore, those of you who are quite clever and intelligent, they have already understood very nicely, and others will also understand after today's lecture, that steels are basically alloys of iron carbide. So, therefore, equilibrium which is important for steel is between iron and iron carbide. Iron and iron carbide, the carbon concentration in Fe3C is 6.678% carbon. That is why I have told previously these diagrams ends at 6.67 percentage of carbon. We do not discuss even what happens beyond this. And as the steels, the carbon concentration do not go beyond 1 percentage. In the actual practice, it can go actually theoretically up to 2.8 percentage, but in actual practice we do not have steel ever more than 1.28% carbon as far as my knowledge goes. So, therefore, the important part of the phase diagram is, that is what I showed last class, is this part. So, the equilibrium which is important for steel is basically between iron and iron carbide. Now, equilibrium which is important for the cast iron is not iron carbide, it is iron and carbon or iron and graphite. So, dotted lines are basically equilibrium between iron and graphite, solid lines are between iron and carbide. So, what are the difference you see here? First of all, you see if you have a carbon or graphite as a second element or second entity component, then your this eutectoid transformation temperature and composition will change. So, normally eutectic transformation temperature is 700 and what 723 degrees Celsius temperature, and composition is about 0.8% carbon, 0.78, 0.8, and if you add graphite, then your carbon this thing shifts to 0.85. Similarly, this transformation thing is also gets modified. This is whatever I discussed about these. What is the modification? Temperature, eutectic temperature, whatever reaction I told you, liquid to gamma plus cementite is between iron carbide. This reaction happens at 1153 degrees Celsius temperature with a carbon concentration of about 4.2% carbon. On the other hand, this another eutectic reaction, which is basically nothing but when the equilibrium is between iron and graphite, that is what gamma plus graphite, and this reaction happens at 1147 degrees Celsius temperature. Carbon concentration is 4.3, right. So, as you see here, both the transformation temperature and composition changes if you have graphite as a second component than iron carbide. This is what I want you to understand very clearly. This can be explained easily from the free energy formalism, which time permits I will also do it. Basically, equilibrium means what? Heterogeneous equilibrium means what? As we discussed at the beginning of this course, is basically you have to draw a common tangent between two curves. One is for the gamma, other one is for the cementite or graphite. So, wherever these common tangents will lie, that is what is the composition given for the stability, right. So, as you see here, if for graphite the maximum carbon concentration which can get into gamma iron is 2.14, not 2.1. 2.1 is basically for iron carbide phase diagram. So, everything gets modified. So, that is the most important thing you have to understand. And when you form graphite directly from the liquid, basically graphite has a different crystal structure, it has a hexagonal crystal structure, as you know. On the other hand, cementite has a orthonormal crystal structure. So, because of change of crystal structure, solubility changes, everything changes. So, basically for all our discussion, which we did not bother about these things when we discuss about steel, because steel graphite does not form at all. Cementite looks like it is a metastable phase, but it can remain thousands of years without transforming into graphite. Basically, cementite should not be present in steel. Cementite is the metastable phase. If you heat it, if you do something, it will transform into iron plus graphite, but it does not happen in steels. As a God's grace, that's why steel is better material. Now, in graphite, that's just a different thing. Graphite, you have a transformation of this cementite to graphite. That is what happens. So, you can either form cementite. Now, in this regard, I should tell you that is why silicon addition is very important. Why? Because silicon actually allows the formation of graphite easily from the liquid. In presence of silicon, graphite forms more easily than cementite. Why it is so? Well, that is mainly because silicon reduces the nucleation barrier of graphite. If you want to form graphite from the liquid, you need to nucleate graphite, and graphite has hexagonal structure, it is a complex things, and also it has a layered structure, so it is very difficult to nucleate. Silicon actually helps formation of the graphite nucleation. There are many reasons for that. How it happens, this is still debatable, but still. But anyway, that is what you should remember. Silicon helps in nucleating graphite from the liquid. That is why silicon addition is very important, and we need a little bit of critical amount of silicon. That is about 1 to 1.2% or 1.5% or maximum 2% silicon is required to do that. That is why most of these cast iron has silicon. Okay, so this is the iron carbide phase diagrams, and before I stop this lecture, let me just explain where everything is given. You please read this diagram. You see A1 temperature, A2 temperature, A3 temperature, ACM, everything is written. A1 47 or 46 is the temperature. A1 temperature is what? Is basically 723 to 27 degrees Celsius temperature. There is something also known as A0 temperature, which is I have never told. and I should tell you A0 is what, because everything should start with A0, A0, A1, A2, A3, ACM. A0 is the magnetic change of Fe3C. Fe3C also become magnetic at lower than 410 degrees Celsius temperature. That is what is the meaning of this. Other than that, please, this diagram you must be very comfortable with it. It is very important diagram for most of the materials we use in the day to day life, like steel and cast iron. Okay, on the other hand, this is the graphite phase diagram. You see here, this is 2.14, this will be 2.14, 6.8 to 4.26. Eutectic transformation temperature is about 736, and this temperature is 1144 degrees Celsius temperature. Okay, anyway. So, in the next class, we will start with the effect of silicon, and I have already given you the idea of the phase diagram. So, let us do that.